theory of continuous medium. Okay, you know what is a theory? What is a continuous medium? Let's start with that word. What is your understanding? Say something.
Flow which happens in a
Continuous medium. Medium means some kind of a
space.
space. Okay, or not space, but okay, let's say some kind of a
Volume.
matrix of atoms or molecules. And it says continuous medium. So we're talking about a description continuous to a medium. What is continuous?
Flow happening in a certain phase.
The flow you talk about is an event. I'm talking about a description called continuous. So what does continuous mean? That's my question. Sorry?
Repeatedly.
Then they would say a periodic medium. Why are they saying continuous medium?
Base description, for example, when we say when we move from inside the water to outside, we change the phases. So when we are inside the water, it will be a continuous.
So again, I don't want to turn this into like an English class, but a medium is like saying it's a. Thank you. A medium it could be anything. It could be vacuum, it could be air, it could be water. So we'll just loosely say a medium represents some kind of material. And we are adding the adjective continuous. So I'm asking what is continuous and also the opposite of what is discrete. Because if you say something is continuous, something has to be discrete. So what about a medium is continuous that we refer to it as theory of continuous media or theory of continuum mechanics. What does the word continuous mean? I want you to start there. If you want, I can give you one hint. You take the most famous statement made by physicist Richard Feynman. He said all the knowledge in this world is contained in one sentence. I'm paraphrasing. Is that matter is made up of atoms and molecules. What do you know about atoms? They are all discrete entities. You can count them in principle. So there are countable number of atoms, but yet when you talk about a continuous medium, what about the atom is not represented in the continuous? Atoms are individual units, they are discrete. Would you agree with me? Right? A material is made up of a certain number of atoms. So in principle, there is an atom, there is another atom, and there is some gap in between. Right? But when I talk about this duster or any material, this table, whatever, I'm talking as though this is a material which has no holes in it. That is what we refer to as continuous. That the medium, I take this table, let's say, I can divide this into half. I can take one of the halves, divide that into half. I can take that, keep dividing it in half. What will I end up with? I'll keep getting halves, but at some point, a given half will not have enough material for, it will have less material than the knife I'm using to chop it. Right? At that point, I'm running into a problem where I'm not really cutting the material, but I'm landing in the space between the molecules of the atoms. You see the contradiction here that real materials or real matter is not continuous. It is made up of very large number of atoms, right? But we think it is continuous. And we go about our lives developing theories, teaching classes, making predictions, and those predictions are actually pretty good. They turn out to be good descriptions of reality. How? How is this seeming contradiction actually working out? See, I'm going to be throwing a lot of questions at you. If you are only going to say the correct answers, we'll never get started. Just say the first thing that comes. Let's start the discussion. Okay, feel free. Yeah.
Because you can mathematically predict the deformation of the material.
That you can, that's what I said, we are pretty successful in describing material behavior using the assumption that matter is continuous. But it is not, you know that. Any material sample is only made up of finitely many atoms, you know this. But yet, if you think that it is indefinitely divisible, that it's continuous, it doesn't have any holes, it doesn't have any gaps, if you make that assumption, it still works very well. Why?
It can't lose its behavior.
Sorry?
It can't lose its behavior.
Um, that, what do you mean by? I don't want to say wrong, but what do you mean?
If you cut out anything else, the two materials they behave same. The properties, what else?
Yeah, you are taking like a sample.
Yeah.
You are dividing it into two halves. The two halves are exactly similar in terms of their properties. You keep doing that. At some point, you are left with atomic clusters. Okay, these atomic clusters, suppose you end up with a half which has, let's say, 51 atoms. That is the last cluster you have. Now, if you divide this, you are going to have one thing with 26 atoms and another with 25 atoms. Or if you divide them asymmetrically, let's say one has 31 atoms, other has 20 atoms. Now, these two start behaving differently. The discreteness of the atoms start becoming important. Okay, so let's keep that piece of information. Okay, I want you all to answer that question. There is this apparent contradiction that real matter is made up of discretely many atoms. But if you make the assumption that a medium is indefinitely divisible, that it's as though it's a continuous blob of material with no holes in between, that thinking, that hypothesis still gets you very good predictions in an engineering sense. Those are two facts. Do you see those? Discrete world, but a continuous thinking gets you good predictions about the discrete world. Okay. Now we want to answer why or how is that working? How is this still working? Okay. When do you call something continuous?
Not in option.
I mean, okay, I will rephrase the question. You see out there, cars are moving, right? You can sit there and count how many cars are going. Okay, but if you look at the same road, same cars, if you kind of zoom out a little, suppose you are doing this not from 100 feet height like now, maybe you are doing this from a helicopter, which is few thousand feet above the ground. Or maybe you are doing this from an aircraft which is 30,000 feet above the ground. These cars, you may not be able to make out the individual details. It will be like tiny dots with a light that are just zipping past here and there. For a second, you can fool yourself into thinking it's not a flow of cars, it's just a flow of fluid particles with a bright spot on each of them. Like each car is like a molecule, and they are just zipping past. They have some light coming out of them, and from that height of 30,000 feet, they actually look like it's like a fluid flow. And if you somehow make it to the International Space Station and look down on Earth, every structure that you thought is an individual structure, which is kind of discrete, will start looking like it's a continuous thing. Right? You can even experience this if you see a bunch of ants. And if you're like me, if you remove your glasses, if your eye power is not that good, you don't get to make out the individual ants, but I know that some kind of black line is just moving. Right? To me, with my resolution, at my height and the size of the ants, it looked like they are a continuous line rather than discrete objects. Can we try to connect this observation of our world that at some scaling, something that looks discrete can appear continuous? with the first question that the world is made up of, or the universe is made up of finitely many atoms, but still a continuum description still works pretty good. Can you connect those two observations? How the latter explains the former.
Material and start to behave like a continuous.
I'll rephrase what you said. You're right. If you zoom out enough, and if you look at a large number of atoms, it will look as though their response is of one unified material and not as a response of a bunch of individuals. It also, what continuation of that, it also is like saying, if you zoom out enough, all the voids between those atoms, they don't matter anymore. It's just that the number of atoms or the mass that kind of is important. But the more you zoom out, you know that when you are looking out there, between each car, there is gap. The cars are not all packed together. And even if you pack them, if you are shipping them in a container across the ocean, when they put them in a container, you know that there is void space in that container. All of you have done solid mechanics or material science in your undergrad. You know that even if it's a FCC or BCC, whatever packing arrangement, there is a limit to how much material you can pack. Void fraction, right? Or packing fraction. So somehow when you zoom out, that gap between or the discreteness stops to matter less. The more you zoom out, the less it matters. The discreteness of the atoms. That coming to you? Okay. So I want to take that highly technical term called zoom out and try to give it more a mathematical foundation. How do you define that zoom out?
Material.
Yeah, include more material, that is of course, but how do you, in a geometrical sense, how do you come up with that scale where you say that at this scale, my material is safely can be considered a continuous medium, and maybe at certain scale or certain, if you are too close to the material. Sorry? Measurement of what? So think about this. This is a experiment that you could even do in principle. Suppose you take, you think about water. What is water? It's made up of H2O, right? You know how H2O is usually drawn. If you take a beaker of water, you can first look at it with your eye, then use an optical microscope, then go to a scanning electron microscope, then go to a transmission electron microscope. And with each better microscope, what do you get? You get to see a smaller region of that sample. Could be water or any material of your whatever you like. Suppose you find the best microscope in the world. It is good enough to distinguish between two water molecules. That is, let's say you can isolate one molecule here and one molecule there. If you are looking at that specimen at the highest possible magnification that's been achieved, you can start to see that there is gaps between the molecules. Okay, but everyday observations. So if you think of a scale, here is, let's say, nanometer, that is 10 power minus 9, and let's say this is picometer minus 12, femtometer 10 power minus 15, attometer 10 power minus 18. These are all length scales. So usually an atom is somewhere here. The size of an atom or the internal dimensions of an atom, something like it's estimated to be around here. And then if you go on in the other direction, there is micrometer, there is millimeter, there is meter, kilometer, and I don't know if there's anything called megameter, we'll stop. Okay. So most of our everyday life takes place around here. Right? You are manufacturing a, let's say you are examining a bone, or you are manufacturing a medical implant or something. You are going to be operating in a size regime where your samples will contain at least 10 power 27 atoms or something. It's the thing that I want to emphasize here is not these number of atoms, but relative to the size of the atom, the scale in which you operate. This is what you said about zooming out. If you zoom out enough, what is enough? This is where you are. And this is where the atomic dimensions are. So if you take a ratio, so I'll call this atomic dimension, I'll call it lambda, and the length scales that I care about in my whatever application, I'll give it a symbol L, lambda divided by L. This ratio, if it is less than 1, what does that mean? It means you have zoomed out enough to meet this condition. There might be these many atoms, but it might as well be an infinite number of atoms. Right? You could put 10 power 40, 10 power 80, it doesn't matter. After a while, they all behave like infinity. You can't get more infinity, you are already at infinity. Okay? So that is one example. That is, you can first you have to think about the word continuous medium is not absolutely there. There is no such real thing as continuous medium. You can take any material, and we are going to be interested in context which can be called continuous. Okay, I'm going to now bug you with two more, or I'm going to ask you for two more examples. Like, can you give of situations where a same material can be treated as a continuum and the same material behaves like a discrete set of atoms, or it behaves in a non-continuum sense? I want you to think, give me an example or two examples. Sorry,
Water flow.
what about it? For the future, you're going to answer, it doesn't stop with two words. You have to explain what you're trying to say.
Like from a tap,
Okay,
we can make it a continuous flow and a discrete flow.
how do you make it discrete flow?
Like by using the tap or totally opening the tap to get a continuous flow.
Okay.
When you like keeping it more tight, it will.
Oh, then you're just talking about flow rate. Your water is still a continuous fluid. You're just talking about adjusting the position of the screw to give a low flow versus high flow. Then in both cases, your water is behaving like a continuous medium. That is not the correct example. Think more. You want to say something?
The film or movie which is captured by camera, which captures lots of pictures all together per second.
Okay, what about it?
When we see that movie, the plot looks like to be continuous, but if we divide the time, for example, we space it into.
So you are saying you are acquiring frames. You are acquiring frames and T1, T2, T3. You are saying if you are in a movie theater, you play a continuous movie, but if you are a movie editor, you get to see the frames. So how do you satisfy this condition?
Some cameras which capture lots of pictures per second, for example, thousands of.
High frame rate, high speed camera. What about it?
So if we take our appreciation, for example, 1 second, per the number of frames per second, for
Sure.
1,000, it will be 1 over 1,000. It won't be that small loss.
See, if you're suppose you are having a high speed camera and getting a video of a tennis ball in a game or a bullet, flying through. Depending on what your frame rate is, you can resolve the motion of a particle. Okay. What is continuous and where does our continuous medium come here?
The movie that we were watching, the film will be the continuous. But if we take the frames and look at the frames, the time intervals, it would be, can be.
Okay, that is called sampling. What you're saying is you have something that takes place continuously. You are sampling discrete events and then making a reconstruction of that. That is, with the recording that's going on now, that camera has a frame rate. Okay, but it's what we think as reality, which is actually that is still being debated by physicists for your information. We think time is a continuous variable. Physicists are still debating, does reality flow continuously or does it go from instant to instant? So let's not go there because even the physicists are not fully come to a consensus. Okay, let's pick something else. I want you to think of, very simply putting, a situation in which your length scale of interest is much larger than the atomic dimensions, and another situation where your length scale of interest is comparable to the atomic length scale or atomic dimensions.
Pixels on a TV screen, here a good example, because the
Tell
more
me.
pixels you have, if you have like a 4K display, for example, you can't distinguish the pixels, it looks like a continuous
It
medium.
actually is similar to what he said.
Yeah.
You are sampling a image with a finite number of pixels, right? So if you have a old school convex lens, you put a candle in front of it, you will get an image on the other side. That is called an analog image because it is exactly a projection of the object onto a screen. But if you put a camera, digital camera, actually the better way to say that is, you do a thought experiment. You capture the image of the candle using a old school analog camera with a film and a digital camera. An analog camera basically exposes the light onto that chemical and it will give you an image which actually practically has atomic resolution. If you can keep zooming on that film, you will be able to get more details because the light carries the information about whatever is on the other side. It's getting recorded on a film by a chemical process. If you come to the digital camera, what is a digital camera? You tell me.
Takes in the light and has a lens that separates.
Lens is common between both the cameras, but the main difference is where you record the light. A digital camera, some of you may know this better than I do, so correct me if I'm off base. But a digital camera has a certain number of pixels or image sensors which capture the light and they basically encode the light. So it basically measures in levels. So you have, let's say, 256 pixels. You will get a distribution of intensities on those pixels, which you then reconstruct later as an image. What the 4K TV you talked about is just has more pixels. The 4K refers to the number of pixels basically. So, like he said, you can capture a bullet with a regular camera versus a high-speed camera. It's just how many frames you're going to get. You are talking about spatial resolution. The more pixels you have, more details you can capture. But that is not fundamentally related to the length scale of interest. I still want you guys to think about two situations of the same material, whether solid or fluid, behaving in a continuous way and a discrete.
So if I get a beaker, enclosed beaker, there is gas in it. If I heat it up, it will get into a temperature, right? So each gas particles, then if we zoom in, each gas particles have different velocity, different kinetic energy. If we measure that, we cannot measure that, but if we want to measure that, will be all different in different directions. But as a whole, if we try to measure the temperature, at some point, the temperature will be same at every point.
Right.
It's continuous. But if it's moving, the kinetic energy is different everywhere. So that's
So if I may use your analogy and say he has that container, sealed container, which is heating up, right? Once it is heated up, let's say you stick a temperature probe, like a thermocouple. What is a thermocouple? It is a tip which senses the temperature. So the gas molecules all hit the probe, and whatever the temperature of the gas is the probe equilibrates with the gas and you read out the temperature. That's how measurement works, right? The probe that he is inserting has a tip size usually that is in this range. You can take a thermocouple probe tip and actually literally look at the two wires being soldered. The solder tip will have a dimension that's about 1 millimeter, maybe 2, maybe half, but about 1 millimeter. So we are here. If you zoom in or think about what's going on at the level of the probe, here is the two wires, here is the probe tip. This probe tip is being bombarded by gas molecules from all sides. I mean, these marks are basically trajectories of the molecules that I am drawing. They basically come, hit the tip, and then get reflected away. If you are focusing your attention to the gas molecules themselves, that is, a molecule travels in a straight line until it meets another molecule. So when it meets another molecule, they crash into each other and they get scattered. And this keeps happening over and over and over. If you zoom down, or if you go down to a size range where your probe tip, let's assume it's not a 1 millimeter tip, it's a nanoparticle whose size is about 100 nanometers. I'll give you a number. So I'm thinking about a particle whose size is about 100 nanometers. And these gas molecules, they travel some distance before they meet another molecule and they get scattered, and they keep doing this. You can ask me how I got this number, but I can show you, but not today, but later. The average distance traveled by these molecules between collisions, it's called the mean free path. It's a number you can statistically calculate, and this number is about 60 nanometers for nitrogen at standard temperature and pressure. Imagine this, you are sitting on top of a nitrogen molecule and you are zipping past objects, and it's like saying I can travel 60 nanometers before I will meet another collision. 60 nanometers on average, sometimes it could be lesser, more, 60 nanometers. And if I'm sitting on top of this particle, and you are zipping by on top of a molecule, I'm sitting here watching you, my extent is only 100 nanometers. And if you are traveling 60 nanometers, to me, that is a discrete event. I can literally see you going past me. It's like we are sitting on Earth. If an asteroid flies by, we can see it. That's similar to that. So in this sense, the same gas behaves like a discrete collision with this 100 nanometer particle to describe the momentum exchange between the gas and this 100 nanometer particle. You cannot use continuum mechanics because you can't call this gas a continuous medium anymore. If on the other hand, you are doing old school fluid mechanics, you have an object which is, let's say, 10 millimeters, you have a flow of gas, the gas goes around the particle. You can describe the flow field, you can describe the heat transfer coefficient, the momentum transfer, everything using equations of fluid flow. That is continuum mechanics. Do you see the difference? The same gas, same material, when the length scale of your interest changes, the description goes from being continuous to discrete, or goes from being discrete to continuous. So now tell me, what is this course going to deal with? From the title of the course, Theory of Continuous Media, what can you infer about where are we going to stand on the scale? And yeah, tell me. Sort of like saying we will always stay in a regime such that the length scales that you will care about is always much greater than atomic diameter. You're doing solid mechanics, right? You could work with samples for your entire life with that are at least a millimeter or bigger. I could also be doing solid mechanics, but I might not be doing the millimeter size samples. I might take nanoparticles like 100 nanometers or 50 nanometers or 10 nanometers and put them between two I forget the name of the instrument which you use to do compression testing. The one where you try to press it at a constant strain. I keep forgetting the name. Don't worry about it. What I'm trying to say is same material at a certain length scale, you can use continuum mechanics to describe. If I am working with iron atoms, okay, you said steel, right? You might be interested in steel. Let's say I work on iron atoms. I'm interested in iron clusters which have only 30 atoms. Same material, you are also doing Fe, I am also doing Fe. But the mathematics I use will be completely different from the mathematics that you will use. Because I work in a discrete world, you work in a continuous. I'll give you one more practical example that I know of. You all know about ceramics, right? Metal oxides, silicon carbide, gallium nitrides, materials like those. Is aluminum oxide a ceramic material? True or false? Sorry? True. Is aluminum oxide a brittle material? True. In common experience, that's what we think. If you have a block of aluminum oxide and you drop it from somewhere, it's going to fracture, right? If you repeat that experiment with a sample size, say 10 centimeter cube, 1 centimeter cube, 1 millimeter cube, 1 micrometer cube, the same outcome will come. You keep crushing it with a compressive force, it will fracture. But I forgot to bring it today, but if you repeat the same experiment with particles that are half a micron and smaller, they undergo plastic deformation. How? Simple explanation is, you take a smaller particle, the number of pre-existing defects can be very small. In fact, you can even produce particles that are defect-free. So you take a half a micron particle and you don't, let's say you don't have any defects, pre-existing defects in those, and when you subject it to compressive loading, it's going to yield and undergo plastic deformation like a regular ductile material. The larger your sample becomes, the chance of defects goes up and you get brittle fracture. Same material, but length scale dependent behavior. Okay? But in my example, it's still both my examples are in the same continuum regime. Even a half a micron particle is still only somewhere here, it still falls within the descriptions of continuum mechanics. If we really want to push the envelope, we have to start approaching atomic dimensions, which we will never do in this class. So all this 1 hour discussion is to say what we will not touch. We are going to be operating this number or this ratio in fluid mechanics, at least this ratio has a name. It's called the Knudsen number. The Knudsen number. The Knudsen number is essentially a comparison between some kind of atomic transport scale divided by the macroscopic length scale. So I write Knudsen number is defined as lambda over L, where lambda is a atomic transport length scale and L is a macroscopic length scale. Usually, whatever we are interested in a particular problem. if I start by saying that this block is my object of interest and I want to apply some load on it and predict its deformation, my length scale of interest is this block, whatever its dimensions are. And since atomic dimensions are so small, almost always we'll be in the continuum regime, except in rare situations where this condition is not met. This is the regime of continuous media. Ooh, so much time for something we won't deal with. All right, so that's why I also want you to read through chapter 1. Just it's a lot of stories, it's a lot of history also about what Newton did, what people after him, discussed and everything. So that is your reading assignment for today. Okay, read through chapter 1. So overall, in a broadest sense, the goal of this course, or this not this course, but the um, but the I want to say paradigm, like a way of thinking. Continuum mechanics, or calling material continuous media, is a way of thinking, and continuum mechanics is a way to describe the deformation, which is like a effect of a material in response, which is the cause, sorry, that's not the cause, in response to an applied state of stress, which is the cause. So the whole field, or the whole topic, is aimed at one thing. If I know what my material is, if I specify what load it is subjected to, I should be able to say what comes after. What is the deformation that comes after? That is what the whole field is about. And this is very fundamental. I've put this in terms of not solid or fluid or material A or material B, but I've said a material. And as you know, material can be in a state of solid-like behavior. I mean, I can simply say solid, but I want to say solid-like behavior because I want you to stop thinking solid is a noun, it's an adjective. Okay, solid-like behavior or fluid-like behavior, and everything in between. So now it's no longer black and white. It's not that solid is on one side and fluid on the other side. You can have materials which have properties in between also. Can you name some materials which look like a solid but have fluid-like behavior, or look like a fluid and have solid-like behavior? So sorry, what?
Yes.
Melted metals, yeah, what about them?
They are fluid, for example, they can flow once, it's very much viscosity.
Isn't that just like a very viscous fluid? I mean, if you grew up on Venus, don't mistake me, you would think lead is a liquid. Yeah, you can think a solid is like a, you can think of glass. Glass is typically called a super cooled liquid. It's like saying if you give it infinite time, it will flow, but you don't have infinite time. You can't give infinite time. So yeah. So what do you want to say in conclusion? Yeah, I want you to give me non-binary examples, situations that don't confirm exactly in one or the other column. Yes.
Lava,
What about lava? Tell.
molten state, when it is flying, like fluid like behavior, it's cooled down, it goes to solid.
You can also add by saying that lava has very high yield stress for shear. It will look like it's static, but it's actually flowing very slowly. It'll take even millions of years for it to make some distance. Same thing applies with many geological events like glaciers or even tectonic plates. They all move, but extremely slow strain rates or extremely slow deformation rates. Okay, more examples. Keep thinking.
Smelting of ice.
He was going to say something. I'll come back to you.
Plasma, like that. Plasma's kind of in between.
You mean the blood plasma? Oh, you're talking about ionized gas.
Yes.
Yes. Okay. Okay.
I don't know for sure, but that's just something I've heard is kind of in between different states. So maybe you could have solid and fluid behavior.
So it is usually like plasma is usually like an ionized gas. It has ions, electrons, even some neutral molecules. Um, Usually it behaves more like a gas. It flows. It has viscosity. It has a pressure. It does pretty much very similar things to a conventional gas or a conventional fluid. I don't know if there could be a way we can think of a plasma being frozen solid. I've not encountered that, because the reason is, if you think of where plasmas usually occur, they are stars and stellar medium. Those are all very high energy objects. You rarely get to see them frozen. Like you can't think of a star being frozen, right? But again, I don't know a lot, or I don't know the entire story on plasma. When you think of neutron stars, black holes, they are also very energetic objects, but they are also gravitationally very strong. So I don't know whether the plasma you are describing there will apply, but I'm not able to judge your answer. Okay.
Smelting of ice.
What about you? Okay, you're talking about phase change now. What you said, what you're saying is a regular material that is known to be a solid changing phase due to melting, or that is not what I'm referring to here. A material in its natural state exhibiting both solid-like and fluid-like behavior. That's what I'm asking you for. You should be able to say something. You're coming from civil engineering, right? With your concrete and your soil mixture, clay and everything. Anyone else?
Blood.
Okay.
Like
Yeah, tell me, you're on to something. Yeah. So blood is usually flowing in your body. It better flow, otherwise we'll all be in big trouble. But uh, it can also stop flowing. How does it do that? How does it clot? You tell me. You're the biomedical guy.
Platelets. There's something that's released that makes the platelets combine together. Get what's released, but those platelets,
They suddenly undergo coagulation and they form what looks like a jelly. Like it suddenly becomes like silly putty. It's like saying your blood has these things called platelets. You should correct me if I'm wrong. And if there is a chemical change or an enzyme change, or in some way your brain tells your blood to freeze or coagulate, those platelets basically rapidly coagulate and form a network which basically stops the fluid behavior, stops the fluid flow, because blood is mostly water, but it also has a bunch of other things which give it that characteristic. So your brain can direct your body to for your blood to clot, and that happens through platelets, right? So the same material, blood, in one moment it can behave like a fluid, and upon some chemical changes can behave like a solid. Another similar example is silly putty. How many of you have played with it? Jelly. How do you make jelly? Take that powder, it's basically cornstarch, you mix it in water, keep stirring. At one point, you have reached a certain volume fraction that the material just seizes, and you get a network formed like a scaffold, and the water is just clinging onto the scaffold. So there is no motion of the water. So you can do this, it will just be like blobbing, but it won't flow. Same thing with clay mixtures or concrete. You can pour it, but after a while it's a solid once the water has evaporated, right? One more example and I'll let you go. Not home, but to the next topic. Almost home, just 10 more minutes. Give me an example of a material that has non-binary behavior. Want to say something? No?
In mud, a similar way that
I already said that. I said clay with water, concrete with water. So think of something else. You said lava. The lava, you can think of it that way. So if you think of fluids like honey or even your Vaseline, the petroleum jelly, try this at home. Take your jelly of the box of petroleum jelly and flip it upside down. Just leave it there. Your jelly is in the container. If you come back after 3 months, all the jelly will be on the lid. It just flows. It looks like a solid. It looks like a cream that you can just take and apply. It looks like a solid, but it flows. And I did this experiment not by intention, but by accident. 3 months later, all the jelly is on the lid. It flow, and I'll bring that maybe next lecture. So the vessel is like this. The container is like this. The lid is like this. When I flip it, all the Vaseline basically accumulated here, and this surface is clean. Clean meaning there is nothing sticking on there. It literally, if you had done this with water, the same outcome you would get, I was able to get it with petroleum jelly. So what seemed like a solid to the eye exhibited classic fluid behavior. It flew down. It flowed down. Okay, so the jelly has both kind of behavior. So if you can think of a yield stress for that material, you can also think of a viscosity for that material. Both exist simultaneously. One last remark about fluid behavior. What is the difference between solid and fluid? How do you define solid and fluid? Or actually, let's define fluid first, and from there we'll define solid. How do you define fluid?
Flowing particles.
That's not how we talk about something like flowing particles can be anything. The car example, cars are flowing. Is that is make it a fluid? No. How do you define a fluid? What is a fluid? I'm sure you have seen this in fluid mechanics at some point.
the atoms are more free to move. They can move throughout the entire medium, whereas a solid, it stays closer to a single point.
That is correct from an atomic standpoint. You're exactly right. The practical way of finding out if something is fluid or solid, I'm asking. Like, I know this eraser is here, and how do I know it's a solid? How do you know anything is a solid? So when I try to apply a shear force on this object, it offers resistance. And if you take this and do this on a block of a ductile material like a metal, iron or something, you apply a shear load, it will deform. You let go of the load. If you're still in the elastic region, it will come back and attain its original dimension. You do repeat the same experiment with water, what will happen? You have, let's say, same volume to volume, same replica of the sample, water, iron. You are having the water in a container and you are having a lid that is touching the surface of the water and you are shearing, you are moving the lid past the surface. What will the water do? It will start rotating, it will start moving, right? Suppose you are color coding the water layers. Suppose you know that you have some oil droplets there that were initially at the top. You did the shearing, those oil droplets would have made like a half rotation and gone to the bottom. You can unmistakably say that the water molecules that were in the top are now in the bottom. Come back to the solid case, you take an iron block, you apply the same force, and you know that the atoms that moved a little bit to the side then came back to the original spot. What is the difference between this experiment and the water experiment? The iron atoms were able to take up a stress and provide a response which was elastic. Elastic meaning they returned to their original homes, original spots. The water could not do that. Correct? Would you agree with me on this fact, on this thought experiment? If you apply a shear stress to a fluid, it cannot sustain it. It cannot offer resistance. It can offer resistance, but it cannot sustain it. It cannot undergo elastic deformation. It has to just undergo permanent yielding. So the way we define fluid-like behavior, this is basically for you to know what is the two limits and then understand that reality exists between the limits. The way we define a fluid is that a fluid is a material which cannot sustain or which cannot which always yields to shear stress. There is no lower limit. It could be the smallest shear force, water will still move. But a solid has yield behavior. Until the elastic limit, it can retrace the deformation. After that, only it will yield permanently. A fluid has no such limit. It has no elastic region. It straight away starts with yielding. So if you draw the classic stress strain curve, here's your classic elastic fluid, at least within the elastic limit. And then you will have the yield and then plastic deformation and then fracture. A fluid's curve starts right here. Whatever this point is, for the fluid, it starts here. It starts with yielding. It cannot sustain any elastic stress. Okay, that's the definition of fluid. And then we just think that, okay, that is true for an ideal fluid, but in reality, every fluid can sustain some amount of shear. So they have some solid-like behavior. So come back to your jelly or your clotted blood. Clotted blood is solid or fluid? It's more like solid because it doesn't move easily. That's what clotting is, right? Same thing with jelly. So what started as a fluid then became a solid. Okay. Question? All right. So I guess that's a lot of semi-quantitative or kind of like broad strokes ideas that I like put in front of you. Now I want you to read chapter 1, which is more or less the introduction to the course. Then from Thursday, let's start with chapter 2, which is basically scalars, vectors, and tensors. So a lot of math from Thursday. Okay. Question? All right, so it's about 6:52. So instead of starting a new topic, I'll start it on Thursday.